Hello everyone, welcome to today's lecture on further system properties. So far, in our Signals and Systems course, we have covered linear and time invariant systems. However, there are further system properties to explore. In today's lecture, we will be discussing stability, causality, memory, and invertibility. Stability is an important system property which is independent of linear and time invariant systems. We will first begin looking at stability in a common example in order to get a good sense of the idea. Look at figure 1a and b. Can you take a guess which one is stable if the input is the applied force x and the output is the angular deviation y from the vertical? Now let's consider that figure 1a and b are pendulums. Gravity applies a restoring force that tends to return the pendulum to the vertical position, and frictional losses due to drag tend to slow them down. Consequently, if a small force X is applied, the resulting deflection from the vertical will be small. The effect of gravity is to apply a force that tends to increase the deviation from the vertical. So a small applied force leads to a large vertical deflection, causing the pendulum to topple over, despite any retarding forces due to friction. Now you probably have a sense that a stable system is one which small inputs lead to a response that does not diverge. Some other examples of unstable systems include a bank account balance. If an initial deposit is made and there are no subsequent withdrawals, then that deposit will grow each month without bound because of the compounding effect of the interest payments. There are numerous examples of stable systems. For example, in the RC circuit in figure 2, let's decide whether or not the system is stable. The first-order differential equations listed in the slide can represent the RC circuit. Assuming positive component values in this equation, the resistor dissipates energy, and this circuit is a stable system. In order to further explore whether or not this RC circuit is stable, please take a look at our accompanying worksheet. If the input to a stable system is bounded, i.e. if its magnitude does not grow without bound, then the output must also be bounded and therefore cannot diverge. In other words, a system is said to be stable in the bounded input, bounded output sense if any bounded input signal is guaranteed to produce a bounded output signal. For a continuous time signal, if the impulse response is absolutely integratable, then the output is bounded and the system is stable. For a discrete time system, if the impulse response is absolutely summable, then the output y is bounded in magnitude. For proof, please refer to page 113 of the textbook, Signals and Systems by Oppenheim, 2nd edition. If we suspect that a system is unstable, then a useful strategy to verify this is to look for a specific bounded input that leads to an unbounded output. Finding one such example enables us to conclude that the given system is unstable. If such an example does not exist or is difficult to find, we must check for stability by using a method that does not utilize specific examples of input signals. In seeking a specific counterexample in order to disprove stability, we might try simple bounded inputs such as a constant or a unit step. For system S1, a constant input x of t is equal to 1 yields y of t is equal to t, which is unbounded, since no matter what finite constant we pick, y of t will exceed that constant for some t. Therefore, we conclude that system S1 is unstable. For system 2, we cannot find a bounded input that results in an unbounded output. We want to verify that all bounded inputs result in bounded outputs. Specifically, let b be an arbitrary positive number, and let x of t be an arbitrary signal bounded by b. We therefore have x of t is greater than negative b or less than b for all t, and y of t satisfies. We conclude that if any input to S2 is bounded by an arbitrary positive number, the corresponding output is guaranteed to be bounded. Therefore, S2 is stable. For system 3, it is obvious that the system is bounded input, bounded output stable if it is less than or equal to 0 and unstable if A is greater than 0. Now you might recall that we also learned about stability while learning about poles and zeros in ENEL 343. Let's see how they're related. The figure on the left is the pole zero plot. Recall that the transfer function represents a system differential equation. Its poles and zeros effectively define the system response. In particular, the system poles directly define the components in the homogeneous response, which can be written in the equation shown in the slides. The transfer function poles are the roots of the characteristic equation. A pole that is negative in the left half of the S-plane defines an exponentially decaying component in the homogeneous response. A pole in the right half plane corresponds to an exponential increasing component, causing the output increase without bound, therefore the system is unstable. In order for a linear system to be stable, all of its poles must have negative real parts. That is, they all must lie within the left half of the S-plane. A system having one or more poles lying on the imaginary axis of the S-plane has non-decaying oscillatory components in its homogeneous response and is defined to be marginally stable. Our next system property is known as causality. A system is said to be causal if the present value of the output signal depends on the past or present values of the input signal. Take a look at the example. The moving average system is causal because, as you can see, the output y of n depends on present values, aka x of n, or the past values of x of n minus 1 and x of n minus 2. In contrast, a system is said to be non-causal if the output signal depends on one or more future values of the input signal. So in the second example, we have y of n being dependent on a present value of x of n, a future value of x of n plus 1, and a past value, x of n minus 1. But due to there being only one future value, the system is automatically non-causal. Keeping in mind the definition of a causal system, it is important to note that causality is required for a system to be operating in real time. All practical systems are causal. Taking a look at the example, in System 1, we can see that there is a delay of 0. Therefore, y of t is produced instantly, as it would in real time. In System 2, we have a delay of 1. Therefore, y of t is not produced until after 1 second, which could not happen in a practical example. So far, we've become pretty familiar with linear and time invariant systems. So how do we define a causal linear time invariant system? As you can recall, the output of a system y of t can be written as the convolution of the input signal, x of t minus tau, and the impulse response of the system, h of tau. For this example, we're going to assume that y of t is causal. Let's set h of tau is equal to 0, and therefore x of t minus tau cannot be equal to 0. What if we set tau to be a negative number? Well, if you plug in a negative number, it's easy to see that the input x of t is actually a future value of input. Therefore, it is non-causal. However, if tau is a positive number, then x can either be a present or past value of input. Therefore, our system is causal, satisfying our initial guess that y of t is causal. This leads us to the really important condition to prove that an LTI system is causal in nature. h of t must be equal to 0 when t is less than 0. A quick example to solidify this idea is the unit step function. If the unit step function is our impulse response, we can see that it's 0 for all t less than 0, and therefore it is causal in nature. So now that we have a better idea of what causality is and a causal LTI system, I want to ask you the following question. Is an ideal low-pass filter causal in nature? Well, as we can recall, the condition that we derived in the previous slide states that in order for an LTI system to be causal, h of t must be equal to 0 for t is less than 0. So, how can we prove that an ideal low-pass filter is or isn't causal in nature? Well, it's actually pretty simple. We can solve for the impulse response of an ideal low-pass filter. When you solve for the impulse response, you'll actually see that the impulse response extends all the way to negative infinity. Therefore, it does not satisfy the condition, and it is not causal in nature. So, we actually cannot implement an ideal low-pass filter in real life. A system is considered to not have memory if its output only depends on the present value of the input. Let's take a look at some examples. In the first example, we have an equation that models an ideal amplifier. It is a static system, as all it does is multiply the input by some constant k. In the second system, we have something known as a square law. Just like the amplifier, it too does not have memory, i.e., it is a static system. As discussed in the previous slide, a system with memory is said to have an output that does not depend on present input values. Such systems are also known as dynamic systems. Many real-world systems have memory. A perfect example is the voltage expression for a capacitor. As you can see in the equation, this is an integrator. The integral present in the equation is what makes this a dynamic system. It is clear that the voltage relies on past values of the current that flowed into the capacitor. The final system property of today's lecture is known as invertibility. A system exhibits invertibility if there exists another system that restores the input signal, demonstrated in the following graphic. However, not all systems are invertible. In the time domain, we can observe an invertible system as convolution, where h of t is the impulse response. Furthermore, in the frequency domain, this can be simplified as convolution becomes multiplication. As shown in the frequency domain, the inverse of a system can be represented as dividing by the transfer function. This fact can also be used to regenerate an expression in the time domain. However, a closed form expression may not exist. Due to this, inverse systems may involve differentiators and other functions that affect stability and bounded input, bounded output, which was described earlier. Lastly, a system is only invertible if it is one-to-one or injective. Thus, a simple test can be performed, as you can see in the slides. Thank you all for listening to our lecture on further system properties. We hope you enjoyed.